In my heart, yes, we are. No, I had it for honors camp doing accuracy and precision demonstrations, and y'all had to shoot a piece of paper.
Is that why there's so much paper behind you?
Yes. I haven't cleaned up yet. Okay, so we are now walking through this because, fire drill. What is the name of this? Ammonium dichromate. Name this one. Say it again. Okay, don't think a polyatomic ion. It's not. Two names. Chromium what? Chromium 3 oxide. Not covalent, right? Nitrogen, cool. Water. All right. So how'd you balance it? 4 in front of the H2. So what did you guys do to balance first? So sometimes that's helpful. Did you say the chromiums were already balanced? You're good. You saw there were numerous oxygens. You saw there were 2 nitrogens on each side, but how many hydrogens? 8. So you saw 8. So then let's go over here and fix that first. That's why you guys said 4. My pen is really off. And then how many oxygens total on the product side?
7.
So 4 plus 3 is 7, right? And then you see 7 over here. It's all good, right? Okay, cool. What's likely going to happen to water here? Split. Use the word that means to break down. Decomposition reaction, right? Just like this was a decomposition reaction, this one is as well. And we can't make pure elements because those are highly reactive. We have to make the 2 gases that compose, or the appropriate forms of these that compose water. So H2 and O2, balance it by putting a 2 in front of the water and a 2 in front of the hydrogen gas. Generally, that whole process is only going to happen through electrolysis. And we will do electrolysis in Unit 10, which is like right after, like February, March area. And so we'll electrocute water and split it and make bubbles. So next one, what kind of reaction is it? Double replacement, calcium and who switch places? Calcium and sodium basically switch places. So calcium gets with phosphate, right? Give me the full thing. Guys, my mark, I'm gonna have to realign my board real fast, but Ca3 parentheses PO4 2 and okay, so sodium chloride. If this were a double replacement reaction, you had to guess if we had a precipitate, and you had to guess which one it was. Who do you think? So sodium chloride able to be dissolved in water. Yeah. Is it precipitating in water? Precipitates are those 2 liquids that come together to make a solid that drops to the bottom. Generally, that's really, really soluble. Like all alkali metals, group 1, they're all soluble. Calcium phosphate, phosphates are actually very insoluble. So that's something we're going over in Unit 2. I just want to do a quick review. You put a down arrow. You do a down arrow to represent something that is a precipitate. Okay, I gotta do this. This is getting on my nerves. Alright, and then you guys have the last one. What's the first? Oh no, sorry. Balance that one. Balance this one for me. Say again. 3, 2, 1, and 6. Good. Okay, and then what kind of reaction is this last one? So we see oxygen, right? That should be the key. Combustion. Hydrocarbons that react with oxygen is a combustion reaction. So this is propane, and you will eventually look into organic chemistry, and you'll see pro means 3 carbons, there's 3 carbons, and then that's surrounded by a saturated set of bonds with hydrogens, so that's a propane molecule. Oxygen always makes carbon dioxide and water. Okay, and so the first thing generally most people do is they balance the C's, the carbons. So then you would put a 3 in front of carbon dioxide, and then most people will go with the hydrogens. So then 8 hydrogens on this side, I need a 4 in front of water. The only reason everybody waits to put the oxygens at the end is because they exist in 2 places, actually 3 places, 1, 2, 3. So you need to get all your numbers pretty well settled before you start attempting the oxygens. So there's 6 oxygens plus 4, so we have 10. So what I'll put here, 5. All right, so we're good with balancing. The only reason I'm doing this now is because these coefficients become our mole ratios. Do you remember that? Yeah. Mole ratios are from a reaction, whereas internal mole ratios came from what? What we did yesterday, right? or N-terminal ratios, the subscripts within the compound. So those are two different things. All right, so along those lines, we also have to attempt with stoichiometry occasionally some percent composition stuff. And so this right here, I don't know that I printed this for you. No, I didn't. So percent composition will be related to dimensional analysis with stoichiometry because sometimes we have to talk about a part of a compound. So whenever I say to calculate the percent composition of something, it's generally just looking at the element of choice or the atom and the number of them. And I'll do an example down here in just a second. So you're going to look at the number of the atoms, its mass, because anytime we're doing percent composition, it's always in terms of mass, not moles. After that, you're going to take whatever that mass is of just the element, and then you're going to divide it by the total mass of the compound, which is the molar mass of the compound, and multiply by 100, and you get your percent comp. Who remembers some of this? Okay. So I'm going to not do the potassium dichromate example. I'm going to go down here. This blue example, as I scroll down, you'll see it's talking about your lab tomorrow. So if you want to, you can do it in your notes or draw it on a separate sheet of paper. But in your lab, in the pre-lab section, it says calculate the percent comp of Epsom salt. And so I'm doing that with you right now. FYI. It's towards the bottom of the pre-lab. It's not in the first 5 questions. It's just in the body of the lab. So am I able to move on down below? Shake your heads, people. Thank you. Okay. So we'll use Epsom salt, magnesium sulfate. What did I call the rest of this? Heptahydrate, right. Magnesium sulfate heptahydrate. And that's going to be our source of magnesium sulfate for our lab tomorrow. Calculate the mass percent of magnesium sulfate, which is the entire thing, not just an element, but actually the entire thing, and water separately in Epsom salt. So here we go. To get percent magnesium sulfate, I need to do whatever magnesium sulfate weighs over the total magnesium sulfate heptahydrates mass times 100. Get your calculator, get your periodic table. Let's go. I'm doing your part of your pre-lab with you, so I think it's good for us to do this together. If you don't have a calculator, there are blue calculators over in the corner. Alvin, I think I have something better though. Unless they're all dead. Here. Anybody else need to borrow a calculator? That one's dead. Oh my gosh, batteries. Okay. Just make sure you know these are in-lows. Just make sure you bring, if you need to borrow it for a longer time, just bring it every day. Use that one for now. This one's dead. I would give you this one, but I don't even have to turn it on. It's a special charger. This was from my class from last year. Can you recognize this from last year? Last semester?
Oh, that's Hansel's.
Is it Hansel's?
Yeah, he puts a Snapchat clip on everything.
Hold on. So I can scan this?
Yeah, and Adam is a
It
friend.
is Hansel's. I didn't even look. Hold on, did Hansel graduate?
Yeah.
Oh. Well, I have his sample. Alright, so magnesium weighs 24.31 plus sulfur, which weighs 32.00 plus 4 oxygens, 16.00. So you're looking at your periodic table for these. I'm just saying them out loud. So MgSO4 weighs 120.31. Anybody else get that? Make sure I'm not butterfingers here. Okay, that's just the mass total of magnesium sulfate over magnesium sulfate. And how do I get the molar mass of this whole shebang? Just add what? 7 waters. That dot means it's a hydrate. It does not mean multiply. Okay, so you're adding to 200 or 120.31. You're adding 7 waters. So that's plus 7 times 18.016. Right. So water is 2 hydrogens and oxygen. So anybody get the final mass there?
126. Wait, after the other thing is
everything is 246.
422, right? Or something.
47.
I did 016, 18.016. Anybody else get that or 472?
Yeah,
Okay. All right, so this is grams total. And then we're going to just take that, divide, multiply by 100. We'll have our percent magnesium sulfate in magnesium sulfate heptahydrate. That's a mouthful. But you sound really impressive when you say it out loud to people. Well, could you please pass me the magnesium sulfate heptahydrate? which is what you take a bath in for sore muscles. Okay. All right, can I get an answer? 48.82. I don't have a actually good number of sig figs here since there is no measurement here, right? There's no measurement. These are all values taken from periodic table. There's no measurement, so there's not a predetermined number of sig figs. So I'm just going to say 48.8. Because if I'm like 48.2275, that's just too much. That's overachieving. Okay, stick with this, and then can we immediately find the percent water without doing this again? Okay, so tell me what it is. Okay, so you're saying 100% is the total, and you're subtracting whatever this was to get 51. I don't know who's calling me in the middle of class. Okay, 51.2% would be water's component. So that's cool. We can do percent comp, and we've already got the first part of our one of the parts of our lab. Give me a thumbs up if you feel comfortable with those calculations. This is how I survey you. And there are more percent composition examples, but I'm sticking with one for now. One of everything, and then from there I'll ask more questions. So can you quickly tell me the formula for this, and then I'll move on. Copper 2 sulfate pentahydrate. Cu. 5 waters. Okay. That would be a good one for your quiz, right? I can ask you questions about hydrates on your quiz. Okay, so whenever we write things, when we write our chemical formulas, we always write them in their empirical formulas if they are an ionic compound. So empirical just means the lowest ratio. So is this the lowest ratio? No. So what's the empirical for this? CH2O. Because C1H2O is the lowest ratio of 6 to 12 to 6. But this is a covalent compound, so we don't always have to write them in their empirical versions. And we have a whole nother lesson on empiricals. I'm not going to go into depth right now. We're going to do that later. But another term for a covalent compound is called a molecular formula or a molecular compound. Terminology, okay? Moving on. Reaction stoichiometry. Here we go. Okay, so whenever we have a reaction stoichiometry problem, there has to be a reaction. You have to read for the reaction. And I can ask you literally to go from mass of something to mass of something else, or moles of something to moles of something else, or mass to atoms or mass to volume, using percent composition. Anything is really good to go here. So let's do one easy example together. That's not a limiting reagent one. And then we'll do a limiting reagent, probably 2 examples, and we're good. Okay? So you guys already have a lot of practice under your belt. It's just now with reactions. So as you read this, take a second to read it. And then tell me the key parts. So as you read it, you should get about 3 words in. You're like, okay, I know the question. What's the question? Mass of. Tell me that formula. Ki. So grams of Ki is the question. I always write down the question first because then you'll never forget where you're going, right? Okay, what's the mass of potassium iodide necessary to completely react with? What's this? That's your given, that's your starting point. This is what you're going to start with because that's the only thing you have to start with in terms of the math, right? So I know I'm going to use that. And it's telling you it's a double replacement reaction. So, Courtney, get me started. What's my reaction?
So it would be Ki plus PV and then 3.
Okay, and we know it's a double replacement reaction. So potassium nitrate and lead 2 iodide, still lead 2, because that's its name, and that means the lead 2 iodide. I think something's just wrong with the end of my word. It's going to get a 2 subscript. I'm going to try to write neat, but this end over here is wonky. Okay, so we have our double replacement. We also have our subscripts doing crisscross rules, and we need a balance. So we need what over here? 2 in front of Ki. Anything here? No. Anything here? 2, and then nothing. We're good. I'm going through balancing and the double replacements pretty quickly. Now, I know I have to start with what? 26.3. 26 or 20.61, and I'm going to write with a better brush. 20.61 grams of lead to nitrate. All right, what is the obvious first step? You can't do anything with grams, right? You have to convert to moles because eventually you want to get from lead to nitrate to potassium iodide. So there's no way to go from A to B unless you have their mole ratio. So before you can even tackle the mole ratio, you need moles. And I will give you guys molar masses. I know you can calculate molar masses, but I do already have them pre-calculated. That is 331.2 grams of lead to nitrate. Okay, now I'm literally out of lead. I've converted from grams to moles. I'm done with the grams of lead to nitrate, and I don't care about lead to nitrate, so I need to convert to who? Who's my question? Potassium iodide. That relationship is a 2-to-1 ratio. 2 moles of potassium iodide are utilized for every 1 mole of lead to nitrate per the reaction balance chemical equation. Good so far? So moles of lead to nitrate cancel with moles of lead to nitrate. We're in moles of potassium iodide. Remember, your question is grams. What's my last step? Right, what goes on top? The molar mass or the mole? Molar mass grams, right? So 166.01 grams of Ki is 1 mole of Ki. And then we calculate. That is 20.66. So the answer is 20.66 grams of lead to our potassium iodide is required to react with all of that lead to nitrate we started with. Who remembers some of those? Stoichiometry. It's now in play with reactions, but that's about it. So this is usually, like, once you get it, you don't forget how to do stoichiometry. This one, it told us one number, and that's it. That's how I knew it wasn't a limiting reagent problem. Whenever they say, oh, you got 20 grams of potassium iodide and 20.61 grams of lead to nitrate, how much lead to iodide could be made? Then you got a predicament. You're like, well, which one do I start with? That's how you know it's a limiting reagent. Do you remember encountering some of those? Some of us maybe a little bit because we are in different classes, different preps. So I do need to do this one. I'll come right back to this one. This one has a percent comp. I will come back. But I'm going to go to limiting reagent first. So the premise is, in a reaction, generally, you have an expensive reagent and a lesser expensive reagent. And the one that's expensive, you don't want to waste any of it. So you have to find exactly how much you need of it so that there's no excess. Well, if there's no excess, it's called the limiting reactant or limiting reagent. Reagent is the term I generally will use. So it's the one that runs out. You have the smallest amount of it. It will run out first. It limits the final product made. The other reactant is the one that we call the excess, because there's an excess amount of it, and it's going to end up being contaminated in the end, and we just throw it away afterwards, and we find another way to use it, because we don't want to have more of this one, because it's contaminated. That's usually the expensive one. But compared to the excess, or compared to the LR, the limiting reagent, there's always more of it. So these two terms will usually be in questions that say something about what's the percent yield. Yield generally, is that talking about a product or a reactant? If I'm yielding something. Product, right? So it's like I'm making something, I'm yielding something. So if you're talking about theoretical yield and actual yield, it's always talking about one of the products, but it'll say like, what's the percent yield of product Z that you can make from this much of one reactant and this much of another reactant, and it won't tell you which is the limiting reagent, which is the excess. So your job is to figure that out. I have a process for you. But in terms of these, I think most of us might remember theoretical is like, it's theoretical, like theoretical physics. Is it always tangible? Is it always something that's absolutely certain? No, it's not probably going to happen 100% like that in real life. So theoretical, I like to call it the La La Land product, like exactly how much you should be able to make. Whereas in real life, we actually have a realistic amount that we make because there's always human error and there's other things that can go on along in the experiment. So it's the actual amount you get in the lab, in an experiment. So lab is actual yield on paper. calculations is your theoretical yield. And so whenever we ask the percent yield, you're combining the two of those by doing actual yield over theoretical yield times 100, and that would be your percent yield. I will tell you, people, we will still mix this up with percent error. It happens. So I'll try to make sure we're focusing on products being yielded. All right, give me a smile or a thumbs up when you have read over and you're comfortable with moving on. So we're going to do question or example 4 on your sheet next. And you're going to want to write this out like on a separate sheet of paper or on your notes that you've been using right now, because you're going to need like half a sheet of paper. And then I'll go back to the two easier ones. So whenever we have a question like this, and you see that there are two quantities given to you, that's usually the one that's like, oh, I'm a limiting reagent problem, right? So first off, can you tell me the reaction? What are the two reactants? Shout them out. Zinc and sulfur. So I'm spacing them out, but I'm going to have some rows beneath them. This is what we're going to do before, during, and after. PDA charge is what we call that. So these two are going to react. Remember, zinc has a 2+ charge, sulfur has a 2- charge. Final? Z and S. Good. No balancing needed. Nothing's diatomic. It's all good. So this, I made this one easy because it's a 1-to-1-to-1 ratio. All right, so what we do first is before the reaction begins, how much zinc do I have? 25 grams, right? 25.0 grams. And you know that in our first steps of any of these stoichiometry problems, generally we take our grams and we convert to moles, right? We can't work with grams. We have to work with moles. So I know I'm going to have to do that here, and I'll do that in a second. You can also see that I have 30 grams of sulfur, and they're mixed together. Okay, how much of this final product do I have before the reaction begins? 0. Nothing. Okay, so B means before, and I'm going to go ahead and convert both of these to moles. I'm going to do it below it because I don't really have a lot of space. So 1 mole of zinc weighs 65.39. Sorry. Okay. 65.39 grams of zinc, and 1 mole of sulfur weighs 32.00 grams. All right, so before the reaction, I have 25 divided by 65.39. Can you give me one more decimal? 0.382. Never truncate too early, because then you'll have rounding error at the very end. Okay, so before the reaction, I have 0.382 moles of zinc. And I have how much sulfur? 0.9. Say again? I got 936. Can you guys do? What do you do? Okay, sorry. I sometimes make mistakes on doing all these problems numerous times, so if I have a slip of the finger. Well, if you do 32.06, is that what you did?
No, I did 32.
Who did 32.06? All right, Levi, tell me yours.
6.
Thank you. Okay, I do estimates in my head, but 32.06 is more accurate. Okay, so then we have this many moles and this many moles. So the trick now is that you have to compare the ratios for what you have. Well, this much you have of zinc, this much you have of sulfur. The ratio is easy. It's a 1-to-1. So for every 1 mole of zinc, I require 1 mole of sulfur. So every 0.382 moles of zinc, how many moles of sulfur do I need? 0.32. Do I have more or less? More, right? I see I have lots more. So what is this one? LR or excess? Excess. Do you see how you can do that comparison in your head? Okay, it's actually very easy, especially for 1-to-1. So you can even do it the other way. I have 0.396 or 936. I require 0.936. Obviously, I don't have enough, so this one's going to be my limiting reagent. So you're comparing them based on the ratio. All right, so before I forget, this one's my LR, and this one's my excess. I don't want to forget because I just did that in my head. So now that I know which one's the limiting reagent, the goal here is the limiting reagent is going to have 0 left at the very end. So during the reaction, something happens, And after the reaction, how much should I have left of the limiting reagent? 0. So this is a subtraction and addition problem at this point. Each of these columns I'm going to be adding or subtracting to in order to show the changes during the chemical reaction. So during the chemical reaction, all the zinc gets used up. So am I adding or subtracting here? Subtracting. I'm subtracting all of the zinc. It all got used up. 382 moles. Well, since this reacts in a 1-to-1 mole ratio, the same exact amount of sulfur is going to be consumed because it's a 1-to-1 mole ratio. So I'm going to, again, subtract 0.382 moles of sulfur because it's a 1-to-1 mole ratio in accordance with the coefficients above. So I know I'm going to have some excess left over here, right? I'll calculate that in a second. Well, then as I'm producing products, I'm adding products. Adding, again, a 1-to-1 ratio, how much? Point what? 382. Okay, and that happens to be the zinc sulfide. So in the end, I have 0.382 moles of the zinc sulfide. I have 0.936 minus that is, I think it's 0.554 moles of the sulfur. And that's it. This entire chart has everything I need for the entire reaction, as well as all the problems. So let's go ahead. Oh, what was our question? How many grams of zinc sulfide could be produced? So I don't have grams here of zinc sulfide, but what do I have? I have moles, so what would I need to do? Just convert to grams. I'm trusting you can convert that to grams. I will tell you the answer. See, 1 mole, 97.44 grams per mole. This side over here is really bad, guys, sorry. Is 37.22 grams. That's how many grams of zinc 2 sulfide that is. And then your second question be, how many grams of excess reactant should remain after the reaction is over? 0.554 of sulfur, convert that to grams, and you get 17.76 grams. Now, I expect that you're showing your conversion there on the AP exam. If you just went from there to there with no work, they wouldn't give you your credit. So just make sure you're showing your work. And I'm trying to model that every time, but my pen is a little wonky. So that's called a BDA chart, before, during, and after. You track your progress from before the reaction begins to after. But this was a 1-to-1. I'm going to do a harder example next. Give me a thumbs up when you're ready to move. Yeah. Mm-hmm. Okay. And these are, I'm recording right now too, so if you want to go back and listen to the example over again, you totally can. Okay. I'm sticking with the necessary stuff right now, and they're probably the examples. So let's try this one. I want you guys to start by writing the reaction. This is example 5. And Arushi, I know your birthday's tomorrow. Sorry. I'm going to bring cupcakes of some sort. Do you have a preference? Chocolate or not chocolate, or not cupcakes? What's your favorite kind of dessert? Oh, you're so picky. Okay, I'll surprise us. I know some of us are allergic to certain things, so. If Alvin, if you have a request, you can tell me the request later.
What?
I said, if you have a request, you can tell me the request later. Okay. All right, reaction. Alvin, what's the reaction, man?
What?
What's the reaction?
C2O3 plus Al
Mm-hmm.
is Al2.
And? Okay, and then balance. Is that it? Okay. We should see that this is a single replacement reaction. Aluminum is replacing chromium. Chromium's getting booted out. Aluminum is taking its place. All right, so before the reaction begins, I have 38.0 grams of chromium 3 oxide and 9 grams of aluminum. And then it says this. Do I write that in my box, in my big BDA box? Or what is this telling me? I'm sure you read the entire question. What is it telling me? Hold on. So use your words. That's the actual yield. AY, okay? Please put that's the AY, that's the actual yield. So, and no, it doesn't say it, but if it says it's actually collected in the experiment, that's the experimental yield. So we're going to look at that later, but keep that to the side. All right, we know there are 0 and 0 of both products before the reaction begins because the reaction hasn't started. What am I doing with both of these? Convert to moles, right. 1 mole of chromium, blah, 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 is 152 grams. And I'm estimating again. If you're going more accurate, you might get one decimal different from me, but this is from memory. That's 250 moles. And then 9 grams of aluminum. 1 mole of aluminum weighs 26.98 grams. That's, and I'm going to record a couple decimals here, 0.33358 moles. Because I know you guys can convert these, so I have done this part. And if you're calculating with me, you can verify. Okay, so I don't have my little division lines here, but okay. So now I have to determine who's my LR. So here's the other trick that I didn't say out loud in the last example because we didn't need to, because we could use logic and look at how to determine it based on like just the 1-to-1 ratio. But the trick is, write this down if you need to, and I'm sure you will. Take the moles you have and divide it by its own coefficient. Whichever one is less has been like appropriated because we divide by its own coefficient. Whichever one is less is then the LR. So I'm right over here. Divide by own coefficient, and then less is the LR. That's the trick, and you can just do that in your head. I don't have to literally calculate on the calculator, which is less. 0.25 divided by 1, 0.333, blah, 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 divided by 2. Who's less? Aluminum. You don't even need to know the exact number. You know it's just less. So then, if you're the lesser, then you are the LR. And if you are the greater one, you are the excess reagent. Okay, so now that I use the LR, what do I do with that? So I subtract the LR amount from the reactants, right? And I add it to the products. Okay, cool with that so far. But now that I have different ratios, I have to employ those ratios. I always have to look at the LR and who I'm comparing it to as I go. So I'll just start with this one because it's easy. I'm subtracting the entire LR, 0.33358. And I know that that means after the reaction, I have 0 of that. I know that's the subtraction, that's how it works. Now, if I'm subtracting the LR from chromium 3 oxide, it reacts with chromium 3 oxide in a what to what ratio? So it reacts with, so if I'm in the chromium oxide row, I look at this one first, and it reacts with this in a 1:2 ratio. You always compare, so the ratio here is 1 chromium 3 oxide for every 2 aluminum. So I'm subtracting the amount of chromium oxide that would be consumed. This is all of this right here is really what we do in a long stretch when we do the stoichiometry way out like that. That's all I'm doing. I'm just doing it in a box now. So 0.250 minus this divided by 2 should give us a small number, 0.0832 approximately. And you'll notice at the end of this, we didn't have to go this far, but I'm fulfilling the entire table just for this example. So, what is my question about? Is it about aluminum oxide or chromium? What was the yield that it gave us for chromium, right? It gave it to us for chromium. So truly, I don't need to fill out this entire column. I don't need to. Yeah.
I'm confused on where you got the necessarily.
Is that,
I got twice that.
did you put the parentheses?
Instead of doing that by half, I put 0.5 moles. Like I multiply the moles by 2 instead of dividing them.
No, so it's not, so it, PEMDAS, right? You gotta do parentheses, all that stuff first. So you need to go ahead and divide this by 2 first. Or in your math work, in your calculator, put 0.250, subtract this times 2 together, divided by 2 together in parentheses. Right, can anybody else verify this is, okay. Did you guys make sure I'm good? Because sometimes I have better fingers. But yeah, it's like you can't do it in 2 separate steps, you gotta do it all together. Okay, so if I were to fill this chart here, I would put plus, because I'm making products, 33358. What would be the ratio I put here?
1 to 2.
Again, 1 to 2, because there's a 1 there, and there's a 2 for the aluminum. And then what am I going to have to put here? Plus 0.3338 in a ratio of 2 to 2. Well, that's just 1, right? No need to actually calculate. So in the end, after the reaction ends, I have 0.3338 moles of chromium. So this is this is what I get on paper in La La Land, so this is theoretical yield. But what's the difference right here is that my theoretical yield currently is in moles, and my actual yield is currently in grams, so I need to get some consistency here. It doesn't matter. You go both the moles or both the grams. I'm going to go to grams because I have math room right here. So 0.3338 moles times the molar mass of chromium, I think is 52.00. That gives us 17.34 grams of chromium. And your yield should always be less than 100% because no one's going to be making more than they should, hopefully. So actual yield over theoretical yield times 100. Actual yield was what? 15.2 grams over the 17.34 grams times 100 is, someone could just say 87.6. 0.7. So is that a good student or a bad student? Decent, right? 85 and up is pretty good yield. If you get like 15% yield, get another day job. Okay? So I just made you solve 3 big problems. I know that's not new to you. Like, not all of this is new. But do you feel better about limiting reagent? Okay. So let me choose which ones for sure you're going to do. Go back and do example 3 that I skipped. Circle this on your paper, okay? And I'll take questions after that. Circle 3, example 3, talks about ammonia. Before I move on, is that a limiting reagent problem?
Yes.
I want you to read it and think for it first.
No.
No, it's not, because it says what? It gives you the grams of ammonia that's made, and then it tells you some grams of nitrogen, and then it says the word excess. So you got to figure out who's the excess? No, you're good. It says excess hydrogen, so you absolutely know. Excess hydrogen means that's the excess reagent. The other one, the 9 grams of nitrogen, is the one you start with, and that's just how you would start a stoichiometry problem. So circle that one. Do 86 on the bottom where it says more, and then let me look at the textbook ones again really quick to see what I want you to do for sure. You can start on example 3 if you want to. Okay, so I'm circling these because I will forget what I told you tomorrow. We're doing example 3 from the lecture notes. We're doing 87 from the Moore reaction stove problem. I'm sorry, 86, not 87. 89, which you'll see is a one that includes a percent. Remember, percents, guys, are just a fraction. Percents can be written just like a dimensional analysis conversion factor, right? So this is 95% Coke. It's 95 grams of Coke over 100 grams of its total sample or whatever compound it's included in. That's going to be utilized for example number 89 on the paper. Okay, and the only one I'll ask for here is 51. Hold on, let me make sure. 51 is the one I'm having somebody present tomorrow. I like to just be on the fly, tell us, 47. So I'm thinking we're okay with stoichiometry. There, of course, are more problems there for you, but if you can do it 4 times, you can do it 4 times, right? So 47 plus the 3 is 42. So 4 problems. That's included there. You need to read over your lab as best you can. You will not be prepping your lab notebook because I have them, but read over it so you know what you're doing tomorrow. There's a pre-lab. If you want to do a pre-lab in your lab groups tomorrow, that's fine. But remember, pacing yourselves is pretty important. So if you want to talk to them today, say, hey, I'm going to try to look at this one, and we'll kind of talk tomorrow, that's fine. If you got as much as you need to. But we have about 5 or 6 minutes left, so work where you can. So I'm going to change the homework before I forget to.